In last example, we showed you how to introduce this spherical shaped classification boundary by introducing one more feature. Actually, in this video, let's give you one more example. This can be also implemented in the Python scalar and support vector machine package. Example 2. This is called polynomial decision boundary. There's a support vector machine. There is option you can choose the optimum polynomial. This can give you the nonlinear decision boundary. Okay, so this is called ellipsoid. Hyperbolid. Parabolid. And basically, you can introduce your phi function not just by introducing one norm, but you can have the a polynomial of quadratic form polynomial terms, x1 square. Suppose you have three features. Suppose x is in R3, which means that x can be equals to x1, x2, x3. Okay, if you have three features, you can introduce this way. A x1 square plus b x2 square plus c x3 square plus d x1 x2 plus e x2 x3 plus f x3 x1 plus g x1 h x2 plus I x3 plus the constant alpha equals to 0. So this will be our high dimensional classification boundary, and our phi function. So in the lifted hyperdimensional case, we can have all kinds of the shapes. We can have the two cones and cylinders and all kinds of the shapes. This gives us very flexible nonlinear classification boundary. Actually, the phi function is just equals to x1 square, x2 square, x3 square. But you have x1, x2, x2, x3, x1, x3, and x1, x2, x3. So this is a phi space. Okay, phi space. Now, our decision function can be any degree of the degree 2 polynomials. And the isosurface defined by this equation is called quadric. So this is called quadric. So, and a linear decision boundary in the phi space imposes a quadratic decision boundaries in the X space. So, linear decision boundary. For example, you could have the suppose we have the surface here. Okay, so and the projection to the lower case will just be a parabola, will be a circle, right? And you can think all kinds of the shaped decision boundary, linear decision boundary in the higher dimensional case. So linear decision boundary in phi space imposes quadratic decision boundary in X space. Okay, and the word quadratic just means an isosurface of a degree 2 polynomial. And in the special case of 2 dimensions, it's also called the conic section. Our decision boundary can be arbitrary ellipsoid, hyperbolic, or paraboloid. When D is large, when D is large, there are order of D square cross terms. For example, in 3-dimensional case, this is just a 3 terms here, right? But suppose you have large feature space, suppose you have 100 features in your data set. So this could be this cross term can introduce the many of the new features. This will imposes a serious computational cost on a classifier like a supported vector machine, because supported vector machines just using the quadratic programming to solve the minimization problem. So high dimension D could impose serious computational cost. Okay, but it might worth to find a good classifier for data, not linear separable. Okay, for example, actually in general D-dimensional case, this phi will be a function from the RD, right? Originally we have the 3-dimensional feature space. Now we transform to D square plus 3D over 2. For example, if D is 3, so this is 9 plus 9 over 2, which gives us 9, right? 9 features, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if all these extra features makes the classifiers overfit or make it too slow, you can leave out some of the cross terms, only include the x1 square, x2 squares. For example, you can restrict some of the cases to be this to be 0 and only leave this second order term. If you do that, your decision boundary can be yes, if your computational is too difficult, try this. Maybe in next video I'll give you one more example.